So this is section 3.2. It is about open and closed sets. So these are two topological properties that you might assign to a set. And the foundation of a lot of the topological properties that we're going to be looking at is the epsilon neighborhood of a point. So recall that the epsilon neighborhood of some number A is just the open interval centered at A of radius epsilon. So it's the collection of all the points that are within a distance of epsilon away from A. And we will refer to this neighborhood as an open neighborhood around A. Okay, so first topic, open sets. Up until now, my guess is that your only exposure to open sets is really open intervals. And so we know those to just be sets that are intervals that contain their endpoints, but this property can be generalized to other types of sets. And the high level is that open sets are just collections of open neighborhoods. And so when I say collections, I just mean union. So you have a bunch of epsilon neighborhoods. They could be of different radii all around a bunch of points, and you take the union of all of them and you get an open set. So that's the high level. The definition is a little bit differently stated. So it says that a set A is open provided for any point A that you select from your set, there has to be an epsilon neighborhood around it that stays entirely inside your set. So here I have drawn a picture of an open set. We're used to open intervals, so that's my set A. And if I select a point, any point inside my set, say this one, I should be able to find a value of epsilon small enough such that the entire neighborhood of radius epsilon around A will stay inside my set. So let's say I make it like that. Notice that any epsilon neighborhood smaller than this one, if I chose a smaller epsilon radius, that would still be in there. But you have to be careful with choosing larger radii because you don't want to extend outside, like past the boundary of your set. So this guy right here is my V epsilon of A. And you're supposed to be able to do this for any number in your set. So I could pick, say, this point over here, we'll call it A1. And notice that as I move the point that I'm looking at, the value of epsilon needs to possibly change. So A1 is closer to the edge of the set than little a is. And so here I would imagine that the epsilon neighborhood that I'm going to get here might be a different value. So maybe I'll call it epsilon 1 of A1. And this is okay because if you take a look at the order of the quantification, you are introducing your A value first, and then you are finding a corresponding epsilon. And so something to point out here is that epsilon may depend on the little a that you pick. And another remark to point out here is what we're saying is that if A is in an open set, then an entire open interval around A is also entirely in the set. So basically, if you have a point in your set, then you've got essentially infinitely many points in a close neighborhood nearby around you that are also in that set. So as usual, when you want to try to understand what a definition means or what a property is, oftentimes it's helpful to think of the negation of that property. So what would it mean if my set was not open? So someone walks up and they say, hey, here's a set, I claim it's not open. What would they need to be able to offer you as proof that you should believe them? So take a moment and pause the video and you can write out the symbolic negation of the definition of open, and then think about it more at a high level and make sure that you're understanding what's going on. Okay, so hopefully you have your negation now. If you just take a blanket negation using your negation rules, what you would need to prove is that there exists a little a in capital A such that for any epsilon I pick, V epsilon of A is not a subset of A. So we really need to find a point in the set such that every epsilon neighborhood of that point contains values outside the set. So, in other words, no matter how small you pick your value of epsilon to be, so you run epsilon down to 0, what you'll see is that the neighborhood you're looking at always lies partially outside of your set. So to make this clearer, let's take a look at the closed interval 0, 1. Now we know sort of naively that this is not an open set because it contains its endpoints, but let's think about which points can be used to show that A is not an open set. And in particular, you can use your intuition about why you think it's not open, the endpoints, for example. So the points that can be used to show that A is not open in this case are exactly those endpoints, 0 and 1. Now, to prove that you're not open, you only need to give one example of a point that has no epsilon neighborhood that stays in the set. So we have a choice here, so I could come up with two different proofs. Let's say I chose A equals 0. The reason why this is a good choice is because this point is on the boundary of my set, meaning it's right on the edge. And so any neighborhood that I try to select that is centered at 0, no matter how small that radius is, I could make this even smaller and go like that, for example. No matter how small this is, do you see what the issue is? Which part of this neighborhood is causing the problem? So you should answer the left side, because notice here that no matter how small you make this epsilon radius, you're always going to have points in the left half that aren't in this closed interval. So no matter what epsilon greater than 0 you pick, the entire left half of V epsilon of the number 0 will lie outside that closed interval 0, 1. The same thing is true, or analogously true, if you look at a neighborhood around the point 1. Since 1 is on the boundary of the set, there's always going to be this right side of any epsilon neighborhood around 1 that causes problems. So here we've got the right side of V epsilon of 1 is outside our interval 0, 1, and this is true. It's very important. This isn't just for one epsilon, this is for all epsilons. If I wanted to write in a rigorous proof for this, then I would be proving this precise statement up here, this precise negated statement. So the structure of my proof, the structure of my proof would follow the format that I would use for there exists an A. So I would say, let A be 0, let epsilon be arbitrary, and then I would need to argue that for any choice of epsilon, I can always find a point in the neighborhood that's not in A. So if I go back down here to my picture, I want to come up with an actual value that I know for sure is not in my neighborhood of 0. Or sorry, that is in my neighborhood of 0, but not in the set. And so I could select, for example, negative epsilon over 2, because remember what these endpoints are of my interval. This is epsilon, this is negative epsilon. If I was looking over on the other interval around 1, I might use 1 plus epsilon over 2. Why is it that we can't use negative epsilon, for example, to show that the neighborhood around 0 is not in my set? And why is it that I couldn't use 1 plus epsilon to show that the neighborhood around 1 is not in my set? The idea is we have to just remember V epsilon is an open neighborhood, so it doesn't contain its endpoints. And the whole idea here is I'm trying to demonstrate that given my epsilon neighborhood, I can find a point in that neighborhood, so it can't be one of the endpoints. It has to be a point in the neighborhood that is not in the set. And so not in the set A, in this case, not in the closed interval 0, 1. So let's write out a proof. So we let A equal 0 and consider any epsilon greater than 0. Then negative epsilon over 2 is in V epsilon of 0, but negative epsilon over 2 is not in the interval 0, 1. Since, if you wanted to explain this, you don't have to, but negative epsilon over 2 is clearly less than 0. So thus, V epsilon of 0 is not contained in my closed interval 0 to 1. And since epsilon was arbitrary, we can say, and so this closed interval 0, 1 is not an open set. So let's see if we can answer a more difficult question. So let's look at another example. So I want you to prove or disprove that the rationals Q is an open set. So in the spirit of good learning, what you should do now is pause the video and try to work on this on your own and think about it and then come back and we'll talk about it. Okay, so in this case, we are going to disprove that Q is an open set. And the high level is that Q is not open since I is dense in R. So let's think about how that works. So, all right, I've got my number line. Remember, if you're going to prove that Q is not open, I need to show that there exists a rational number. So remember, that point has to be in my set such that no epsilon neighborhood will contain entirely rational numbers. So I'm going to write that down. So find a rational number such that, here, and we'll call that rational number R, such that no epsilon neighborhood around R contains only rational numbers. Because remember, if you were to be open, you should be able to find an epsilon neighborhood that stays entirely inside the set, which in this case is the rationals. So you might think about, for example, which points might be good candidates to use to disprove the openness of Q. And it turns out any R in Q can be used to show Q is not open. If you go back to the previous example, we were only able to use the endpoints, a equals 0 and a equals 1, because those were the only points that were on the edge of our set. But if you think about it, if you were to plot the rational numbers, you'd just be plotting a bunch of points, and every single point would be sort of quotes on the boundary of that set. So let's say I picked, for example, I'll just pick the number 1. So I pick the number 1. I'm going to put an arbitrary epsilon neighborhood around it. So here's 1 plus epsilon, here's 1 minus epsilon. And I need to figure out a point, or at least understand conceptually why it is that no matter how small I make epsilon, there are always going to be numbers in this neighborhood that are not rational. Now, I can't necessarily say, like I did in the previous problem, I can't necessarily say that 1 plus epsilon over 2 is going to be an irrational number, because remember, my argument needs to work for any value of epsilon. So if epsilon was rational, then 1 plus epsilon over 2 wouldn't be a good counterexample to show that my neighborhood leaves Q. But instead, what we're going to do is we're going to use the density of I in R to claim that there has to be some number between 1 and 1 plus epsilon, for example. So there has to exist some little I in the irrationals such that 1 is less than I, which is less than 1 plus epsilon. That's just using density. So we're not actually going to say which point it is this time, the way we were able to in the proof of the closed interval 0, 1 not being open. But here, we're going to be able to instead assert the existence. So this is a non-constructive existence proof. So let's say we go down here and we write our proof. We can let A be 1. or any other rational number. But remember, we just need one counterexample to show we're not open. And then we let epsilon be greater than 0. Since I is dense in R, there has to exist an I in the irrationals such that 1 is less than I, which is less than 1 plus epsilon. This means I is in the epsilon of 1, but I is not in Q. So what we're really saying here is that V epsilon of 1 is not a subset of Q. This proves Q is not open. Just to make sure that we're being careful, I'm going to have you answer this question. Can pi be used to prove that Q is not open? So you can pause your video and think about that for a moment. And you should have come to the conclusion that the answer is no. Pi is not in Q. To show a set is not open, the point you use must be in the set. We only care about points in the set. We're trying to show that every point in the set has an epsilon neighborhood. And if you can't do that, it's because there's a point you find from your set that has no epsilon neighborhood. And that's how you would prove that a set is not open. So here we're not going to use pi or any other irrational number simply because we're trying to look at whether or not Q is open, which means we only consider points in Q when asking that question.